Let us continue molecular orbital theory. In the molecular orbital theory, we are going for pp combination. So now we will consider p orbitals. We are considering an atom. In the atom, we are considering p orbitals in a particular shell. Okay. So one p orbital that then will take internuclear axis. Internuclear axis is a z axis. We will take this internuclear axis. We have considered z axis. It need not be always z axis, even x axis also we can take. Okay. Now we will consider p orbitals. P orbitals in the sense particular shell we have to consider. Particular shell. In that p orbital we are considering, suppose pz orbital. Okay, it is pz orbital. It is one atom. Another atom pz orbital. Another atom pz orbital. Okay, this principal quantum number, this principal quantum number remains same. Okay, then we have to say nucleus of the atom. Nucleus of the atom. Then we have to give sign we have to give. Sign we have to give for lobes. Shy sign. Here positive means here negative. Suppose here positive means here negative. Then it is going for what in the sense linear combination. These two p orbitals going for linear combination. Linear combination in the sense one is addition overlap, another one is subtraction overlap. Linear combination in the sense one is addition overlap, another one is subtraction overlap. Okay. Now these two p orbitals undergo linear combination. That means addition overlap. One p orbital, another p orbital undergoing addition overlap. Now we will give nucleus of one atom, nucleus of another atom. Then we will give sign. Sign how to give in the sense, see that addition overlap means overlapping lobes should have same sign. So these two lobes are overlapping. Therefore, if you give positive, here also you give positive. Otherwise, if you give negative, here also you give it negative. Overlapping lobes should have same sign. Here positive means here negative. Here positive means here negative. Okay. This gives what in the sense addition overlap. So addition overlap in the sense now it will result a molecular orbital. It is resulting what in the sense molecular orbital. Okay, so we got a molecular orbital. Now here nucleus, here nucleus. Okay, so this is what in the sense bond molecular orbital. Here the overlapping takes place along the internuclear axis. Therefore sigma molecular orbital. P orbitals involved in linear combination. Therefore p. Suppose if it is from second shell, if it is from second shell, then we will say sigma 2pz. We can say this, we can say sigma 2pz. Okay, then we will see about subtraction overlap. The two p orbitals, undergo subtraction overlap. It is one p orbital, then it is one p orbital. Two of p orbitals undergo subtraction overlap. Okay, it is a nucleus of one atom, it is a nucleus of another atom. Now we will give the sign. We will give for this overlapping lobes. For this overlapping lobes we have to give opposite signs. Here positive means here you have to give negative sign, you have to give, then only subtraction overlap. Subtraction overlap means overlapping lobes should have opposite sign. It is positive sign means here negative sign. Here positive means you give negative, here negative sign, therefore you give positive sign. Now they are going for overlapping set. So what you will get, we will see. Now one lobe is like this, another lobe is like this. One lobe is like this, another lobe is like this. Okay, now we will give the nucleus of one atom, nucleus of another atom. Now we will give the sign. Sign we will give it. Okay, here what sign means a negative sign. That negative sign will give. Here positive sign that we are giving. Here negative sign, that here positive sign. Okay, now in between two nuclei, probability of finding electron cloud is low, but left side of this nucleus probability of electron cloud is high. Right side of this nucleus, probability of finding electron cloud is high. That means in between two nuclei, probability of electron cloud is low. That means here if you draw a plane, you will get a nodal plane. That means electron cloud is not there. Therefore this situation is unfavorable for bonding. Therefore it is a anti-bonding molecular orbital. It is called anti-bonding molecular orbital. Why sigma? In the sense overlapping takes place along the internuclear axis. Therefore sigma we said. Star in the sense it is anti-bonding molecular orbital. That's why 2pz in the sense 2pz atomic orbitals undergo linear combination. Sorry. Therefore, two 2pz atomic orbitals on linear combination gives sigma 2pz and sigma star 2pz. Sorry. What about their energies? Sigma 2pz energy and sigma star 2pz energy, that we will see. This, it is bonding molecular orbital. Bonding molecular orbital energy will be lesser than that of atomic orbitals. Okay. Therefore sigma 2pz, sigma 2pz energy is less than energy of 2pz orbitals. Because here how the probability will be there means, here probability of finding electron cloud will be high when compared to total probability of these two. Therefore this stability is more when compared to these two. Therefore this energy is less when compared to these two. Okay. Now we will see energy of sigma star 2pz. We will see energy of sigma star 2pz with the energy of 2pz. We will see here. Here what is that? This place is what? Nodal plane. Nodal plane means chi square is 0. Chi square is 0 means it is not favorable for bonding. Here chi square is 0. Here chi square is there. That means this situation is what? This situation is less stable when compared to this situation. Therefore this energy is less when this energy is more when compared to this energy. Therefore how the energy will be there means like this. Then how the energy of sigma star 2pz and sigma 2pz will be there, that will see. Energy of sigma 2pz, energy of sigma 2pz and the energy of sigma star 2pz, how it will be there, that will see. This is antibonding, it is bonding. Therefore it is stable, it is unstable. So it is having low energy, it is having high energy. Therefore energy will be like this. Sigma 2pz will have less energy when compared to sigma star 2pz. Sir, now so for what are the atomic orbitals undergoing linear combination to give molecular orbitals? We have discussed in the sense one is 1s atomic orbitals on linear combination gives, we said sigma 1s sigma star 1s, we said. Then 2s atomic orbitals on linear combination, we said sigma 2s sigma star 2s, we said. Then now we said 2pz atomic orbitals. 2pz atomic orbitals on linear combination gives sigma 2pz and sigma star 2pz. Okay. So we got these are the molecular orbitals. Now energy of atomic orbitals, we'll see 1s less than 2s less than 2p. Okay. Now energy of molecular orbitals, sigma 1s less than sigma star 1s, sigma 2s less than sigma star 2s. Then sigma star 2s and sigma 2pz, if you see 2pz will have higher energy. Okay. Sigma star 2pz will have still higher energy than sigma 2pz. It is a energy of molecular orbitals. Sir. Next, now in the atom, p subshell is there. P subshell in the sense that is having three p orbitals. One p orbital we discussed, that is pz orbital we discussed. What about py orbital and px orbital? That we will see. Now, here internuclear axis we have considered z axis. It need not be always z. We can take even x axis also we can take. Okay, sir. Now we will consider now pz orbital is over. Now we will take py orbital. We will take that py orbital is perpendicular to internuclear axis. Okay, sir. Now we are considering py orbital. Py orbital is perpendicular to internuclear axis. Perpendicular to internuclear axis. That means internuclear axis means z axis. Perpendicular to z axis. Okay. Now we will consider one py orbital. It is what means one py orbital. Suppose two py orbital. This is it is from one atom. From another atom, two py orbital we will consider. From another atom, two py orbital. Okay. From another atom 2p orbital we have considered. Now we will say nucleus of this atom, this nucleus of this atom, this atom nucleus we said. Now we will give sign, we will give a, suppose if we give positive sign, you give negative sign here. Okay, suppose if you give positive sign, you give negative sign. One lobe will have positive sign, another lobe will have negative sign. Okay, now we have considered two 2py atomic orbitals. Okay, now these two 2py atomic orbitals from two atoms, perpendicular to internuclear axis, that is z axis, internuclear axis, but they are they are parallel to each other, Okay, how we have taken, you have got an idea. Sorry, the now this 2py orbital is from one atom, this 2py orbital is from another atom. These two 2py orbitals, how it is there, perpendicular to z axis, internuclear axis, but they are parallel, like this is there. Now they are going for linear combination. Linear combination in the sense, two things possible. One is what, in the sense addition overlap. One is addition overlap, we can say. Another one is subtraction overlap, we can say. Another one is subtraction overlap. So one is addition overlap, another one is what, in the sense subtraction overlap. So now we will see regarding addition overlap, we will see. Okay, how the addition overlap will be there. Okay, this is one p orbital. Next, it is another p orbital. Okay, they will go for lateral overlapping. Okay, now two p orbitals undergoing addition overlap. In the same way, these two 2py orbitals are undergoing subtraction overlap. This is one p orbital. This is another p orbital. Okay, so p orbitals undergoing subtraction overlap here. Okay, now we will give a nucleus. We will give nucleus of one atom, nucleus of another atom. Okay, now nucleus of one atom, nucleus of another atom. Okay, we have considered like this. Now we will say internuclear axis. Internuclear axis we will draw. Okay, we have drawn internuclear axis. Now you see how the overlapping takes place. Overlapping takes place above the internuclear axis and below the internuclear axis. That means it is called a lateral overlapping or sideways overlapping. Result what, in the sense pi. Result what, in the sense pi. Okay, overlapping takes place along the internuclear axis means sigma. Now here we will see. Here we will take internuclear axis. It is the internuclear axis. Now overlapping takes place here, that is above the internuclear axis. Here see, overlapping takes place below the internuclear axis. So overlapping takes place above the internuclear axis and below the internuclear axis. This gives what, in the sense pi. Sir, now we will give sign. We will give sign of lobes. We will give. Okay, lobes sign we have to give. Okay, here suppose you are giving positive sign, then give positive sign in this lobe also. These two lobes undergoing overlapping. Overlapping lobes should have same sign, then only addition overlap. Okay, so in this lobe positive sign means in this lobe also you have to give positive sign. For both lobes you have to give same sign. Okay, suppose if you want to give negative, give it negative. Here also negative. Like this you have to give. Okay, so we have given positive here, so here also positive. These two lobes undergoing overlapping, therefore these two lobes should have same sign, then only we can call this as a addition overlap. Sir, above lobe is positive means down lobe is negative, therefore here also negative we have to give. Okay, same sign, therefore addition overlap. Okay, this is also addition overlap. Sir, so they are undergoing addition overlap, therefore we are getting a molecular orbital now. Okay, it is a nucleus of one atom, it is a nucleus of another atom. Okay, so we have given nucleus. Then now see that above overlap results, that above overlap is like this, then the below overlap is like this, below overlap is like this. Okay, this above is having positive sign, this above lobe is having positive sign, below lobe is having negative sign. Okay, this is called a pi molecular orbital. This is called a pi molecular orbital. Addition overlap in the sense bonding molecular orbital. Okay, therefore it is obtained by 2py atomic orbitals. Therefore it is pi 2py. This is called what in the sense pi 2py molecular orbital. Okay, this pi 2py molecular orbital. Now we will see regarding this. Now, in this case, for this lobe, we will give positive sign. Then give opposite sign to this lobe. Then only subtraction overlap. Okay, subtraction in the sense opposite signs should be there. Here positive means here we are giving negative. Here negative means we are giving positive here. So subtraction overlap. This is giving what? This overlapping is destroying. It is subtraction overlap means overlapping part is getting destroyed. Therefore, how it will be there? We'll see. It is a nucleus. It is a nucleus. Now the lobes become what in the sense one lobe this side, one lobe this side, one lobe goes this side, one lobe goes this side. Okay, like this it will go. Therefore because it is a destruction overlapping, destruction in the sense resultant is what? Zero. Therefore here this lobe is positive sign, for this lobe negative sign, for this lobe negative sign, for this lobe positive sign. Okay, so sign we have given. Now here how the probability is there means 0. Here probability is 0. Nodal plane. This part is nodal plane. Okay. So this is anti-bonding molecular orbital. Therefore pi star, and it is obtained from 2py. Therefore pi star 2py we have given. Okay. So pi 2py, pi star 2py. And this orbital, this we have given. Okay. So pi 2py molecular orbital, pi star 2py molecular orbital. So 2py atomic orbitals and linear combination gives pi 2py and pi star 2py set. How the energy will be there? Energy of this and energy of this, how it will be there? This energy will be lesser than that of this energy. Okay, this energy will be lesser than that of this energy. So energy of pi 2py is less than energy of pi star 2py, because pi star in the sense anti-bonding, so stability is less, it is bonding, stability is high. Therefore this energy is low, this energy is high, like this we can say. Next we will go to px orbital. Okay, now we have seen here py orbital, we have seen here, we have seen pz orbital, we have seen. Now we will go for what in the sense px orbital we will take. Now we are taking px orbital. How px orbital will be there, that we will see. Okay, now we will take a, this is a one px orbital, it is one 2px orbital, this is a one 2px orbital. Okay, 2px orbital. How these two 2px orbitals are there? Okay, these two, these two 2px orbitals, these two 2px orbitals from two atoms, from two atoms, from two atoms means this 2px orbital from one atom, this 2px orbital from another atom. Okay, another atom means it may be same or different, whatever the thing. Okay, so these two 2px orbitals from two atoms, okay, are perpendicular to internuclear axis, perpendicular to internuclear axis, that means z axis. So they are perpendicular to internuclear axis, we can say. And perpendicular to what in the sense y axis, perpendicular to 2py orbitals, perpendicular to 2py orbitals. Okay, perpendicular to 2py orbitals, but they are, they are parallel to each other, but they are parallel to each other, we can say. Therefore parallel in the sense they will go for what? Lateral overlapping. Lateral overlapping means pi bonding. Okay, therefore now they are going for linear combination, they are going for linear combination. Linear combination means two things possible. One is addition overlap, one is addition overlap, another one is what means subtraction overlap. Okay, subtraction overlap. Therefore it is giving pi to px, it is giving pi star to px, pi star to px, like this we discussed. Okay, therefore two 2px atomic orbitals on linear combination gives what in the sense pi 2px and pi star 2px. How the energy will be there means energy of pi 2px is less than energy of pi star 2px. Okay, so now we got about this. Now we will consider conclusion. Conclusion will go. Now we will take 2p orbital. 2p orbital in the sense 2px, 2py, 2pz. It is from one atom. Now from another atom, 2px, 2py, 2pz we will consider. 2pz we have considered. Now these two go for linear combination. Now linear combination possible. Linear combination we considered. On linear combination, what happens means one is addition overlap, another one is subtraction overlap. So addition overlap and another one is what means subtraction overlap. Addition overlap in the sense 2pz atomic orbital give sigma 2pz and sigma star 2pz. 2py atomic orbitals give pi 2py and pi star 2py. 2px atomic orbitals will give pi 2px and pi star 2px. So like this molecular orbitals possible. Okay, so 2p atomic orbitals on linear combination gives what in the sense like this molecular orbitals. How the energy will be there? How the energy of these orbitals will be there? So first we will see this sigma and this pi we will see. What about energy of these two? That we will see first. Okay, so energy of this 2pz, that means sigma 2pz, and energy of pi 2py, that we will see. Energy of sigma 2pz and energy of pi 2py, that energy we will see now. Okay, so now we have taken here. 2py atomic orbitals go for lateral overlapping here. Here what overlapping possible in the sense? Lateral overlapping. Lateral overlapping possible. So now in this case 2pz atomic orbitals going for what overlapping means end on end overlap, otherwise axial overlap. Axial overlap. Okay, axial overlap. Axial overlap means overlap takes place along the internuclear axis. Okay, overlap takes place along the internuclear axis. It is called axial overlap. Okay, sir. Here overlap takes place sideways overlap. It is called lateral overlap. So what about this energy? What about this energy when compared to this energy? That's what we have to see. What about these two energies? That we have to now discuss. Okay. So now we will see axial overlap we are seeing, and the lateral overlap we are seeing. These two overlap we have to compare. Okay. Axial overlap we will take. Axial overlap in the sense it is one p orbital. This is one p orbital. Okay. This is called axial overlap. Then lateral overlap we will see this one p orbital. This is one p orbital, lateral overlap. Okay. Now we will see here in this place. In this place, overlapping takes place. Overlap takes place at one end. Okay. So during overlapping, how the probability of electron cloud will be there? Here, probability of electron cloud will be high. Here, probability of electron cloud will be low. Probability of electron cloud will be low. Okay, during overlapping time. Okay, here in this end, in this p orbital, in this end, probability will be high. In this end, probability will be low. Okay, before overlapping, how the probability will be there, that we'll see. Okay, now we are considering p orbital before overlapping. How it will be there means here probability of finding electron cloud, will be equal. Okay, probability of finding electron cloud in this lobe and in this lobe will be equal. Now we will consider axial overlap in the sense overlapping takes place along the internuclear axis. Now this is one p orbital, then it is another p orbital. Two p orbitals undergoing overlapping. Now how the probability will be there. Probability at this end, probability at this end, and probability at this end, probability at this end. How it is there in the sense, probability will be high, probability will be low. Okay. Before overlapping, probability will be equal. Before overlapping, probability in these two lobes will be equal. During overlapping, what happens means here probability becomes low, here probability becomes high. How do we say that? Now you see. Here, this is a 2pz atomic orbitals undergo axial overlapping and the molecular orbital is resulted. Now see, this lobe is small, but it is big. It is small. What does it mean? It is small in the sense probability is low. Here big in the sense probability is high. Here small in the sense probability is low. Therefore, this p orbitals, but before overlapping, how the lobe is there? This size and this size same. Therefore, here probability same. During overlapping, you see, due to overlapping, what is resulted? This is a resulted. Here big size, overlapping is here big size. That means probability is high. Here probability is low. Okay. That means this is favorable for bonding. This is favorable for bonding. Okay, sir. Now we will see regarding this. So here probability is high, here probability is low, sir. So this overlapping gives what in the sense sigma 2pz. Okay. Now we will see regarding a lateral overlapping. How the lateral overlapping is there, we will see. Now this is a p orbital. It is another p orbital undergoing lateral overlapping. Okay, sir. In this overlapping, how the probability will be there, we will see. In this lobe probability, in this lobe probability, how it is there. Here probability will be equal, because it is sideways overlap. Both lobes undergoing overlapping, and also you have to understand that here overlapping extent, here overlapping extent. How it will be there means extent of overlapping, that is above and below. That is above and below. How it is there means equal. Above and below will be equal, we have to say. Okay. So extent of overlapping, above part and below part, how it is there means equal is there. Equal manner it is there. Okay. So extent of overlapping, this above and this below will be equal. We can say. Now this is resulting what in the sense pi 2py. Now you say that now we will see the probability in these two places. Let us compare. So here overlapping part probability. Okay. Here overlapping part probability. That if you see here probability is high, here probability is low. Okay. Here in this overlapping part, probability of electron cloud will be low. In this overlapping part, probability of electron cloud will be high. Therefore, in this case, extent of overlapping will be high. Here in this case, extent of overlapping will be low. Therefore, this will be extent of overlapping is higher in the sense this molecular orbital will have higher stability. This molecular orbital will have lower stability. This higher stability in the sense this energy will be low, this energy will be high. Okay. Therefore, sigma 2pz energy will be low, whereas pi 2py energy will be high. Okay. So like this energy will be there. Okay. So energy of 2pz is what in the sense less than that of pi 2py. So energy of 2pz is less than that of pi 2py, we said. Okay. What about pi 2px and pi 2py? That energy we'll see. Okay. Now 2px orbital undergoing linear combination to give pi 2px and pi star 2px. Here lateral overlapping. Okay. Then 2py atomic orbital undergo linear combination give pi 2px, pi star 2px. So Now what we are discussing in the sense, we are discussing about pi 2px and pi 2py. Now see here 2px atomic orbitals undergo linear combination. Here 2py atomic orbitals undergo linear combination. 2px energy, 2py energy remain same. 2px shape, 2py shape remain same. Only orientation, it is x direction orientation, it is y direction orientation. Orientation is different. Okay, therefore here extent of overlapping remains same. Therefore this energy and this energy, how it will be there? Remain same or different? Okay, that we'll see. Now we have to discuss about 2px and pi 2px and pi 2py we have to discuss. Okay, so pi 2px and pi 2py we want, that energy we want. Okay, here 2px atomic orbitals undergo linear combination. Here 2py atomic orbitals undergo linear 2py atomic orbitals undergo linear combination. Now this energy is equal to this energy, atomic orbitals energy. Now this size is equal to this size. This shape is equal to this shape. What is different? Orientation is different. But orientation, if you see, orientation is different for these two. Why different? It is x-axis orientation, it is y-axis orientation. Therefore, linear combination. They are going for linear combination. They are going for linear combination means extent of linear combination remains same for both. Therefore, stability for both, how it will be there, remains same. Therefore, energy of both, how it will be there, remains same. Therefore, pi 2px energy is equal to pi 2py energy. Energy of pi 2px is equal to energy of pi 2py, we can say. Okay, therefore we can say this 2px energy and 2py energy will be equal, sir. Therefore like this is there. Okay, now we said like this. Now we will go for this sigma star to pz, pi star to py, pi star to px. We know that pi star to py is equal to pi star to px, we know. Pi star to px we know. What about sigma star to pz? Sigma star to pz, that will see. Sigma star to pz with pi star to py, that point we have to see. Okay, sir. Now we will see regarding this axial overlap we have taken, lateral overlap we have taken. Okay, axial overlap, lateral overlap. Here before overlapping, probability will be equal. Probability will be equal. Okay, now we are discussing about what in the sense sigma star to pz, pi star to py, that we are discussing. Sir, it is a star in the sense anti bonding molecular orbital. Therefore how the probability will be there, that point we will see. How the probability and how the extent of overlapping, that will be there, that point will see. Here probability will be high, here probability will be low, because it is giving anti-bonding, isn't it? Therefore here how the probability will be there means here probability will be low, here probability will be high, because anti-bonding molecular orbital at overlapping part, probability of electron cloud will be low. Okay, sir. Next therefore like this is there. Okay, it is giving sigma star. Okay, next here extent of overlapping above and below will be equal, there is no doubt. Okay, now we will see the probability at the overlapping part, these two cases. Here probability at overlapping part will be low, here probability at overlapping part will be high, like this will be there. Therefore extent of overlap, where will be low, where will be high. That if we say extent of overlap will be low here, extent of overlap will be higher. That means actually extent of overlap in the sense, will be higher, will be low. We said the probability will be low here. That means extent of overlap is high towards anti-bonding. Okay, extent of overlap is low towards anti-bonding. Set. Now we will see stability of sigma star and pi star. We will see this stability we will see in both cases. So here extent of overlapping towards anti-bonding is high, therefore stability is low. Therefore energy is high, energy is low. Sorry, we said probability low here. Then why do you say extent of overlapping high means extent of overlapping towards anti-bonding? Okay. Therefore, here extent of overlapping towards anti-bonding is high. That's why probability is low when compared to this. Okay. Here extent of overlapping towards anti-bonding is high. That's why probability is low here when compared to this. Therefore, this stability is low when compared to this. Therefore, this energy is more when compared to this. Okay. Therefore, we got about this energy. This energy is greater than that of this energy. So we got energy of this set. So how the energy of this set will be there, we got an idea. Okay. Therefore, energy order will see sigma 2pz is less than pi 2px is equal to pi 2py. Okay, less than pi star 2px is equal to pi star 2py, less than sigma star 2pz. Okay, sigma star 2pz. It is the order of energy of molecular orbitals. Now we will give the overall order. Overall order we will give it. Okay. Now 1s atomic orbitals on linear combination gives sigma 1s, sigma star 1s. 2s atomic orbitals on linear combination gives sigma 2s and sigma star 2s. Then 2p orbitals in 2pz atomic orbitals on linear combination gives 2p sigma 2pz and sigma star 2pz. 2px atomic orbitals on linear combination gives pi 2px and pi star 2px. Then 2py atomic orbitals on linear combination gives pi 2py and pi star 2py. Okay. So we got molecular orbitals from atomic orbitals. Okay. Energy of atomic orbitals, how it is there means 1s less than 2s less than 2p. It is for atomic orbitals. What about for molecular orbitals? That we'll see. Sigma 1s less than, sigma star 1s less than, sigma 2s less than, sigma star 2s less than, sigma 2pz less than, pi 2px is equal to pi 2py less than, pi star 2px equal to pi star 2py less than sigma star 2pz. So how the molecular orbitals energy is there, you have seen. Okay. So energy of molecular orbitals like this present. So we got energy of molecular orbitals here. So next we have to go for what in the sense molecules we have to see. For molecules, how the energy of molecular orbitals is there. For each molecule, how it is there, that we have to see. Now if you take F2 molecule, here how the energy of molecular orbitals is there means like this is there. Energy of molecular orbitals will be like this. So then I will take O2 molecule. In the O2 molecule, how the energy of molecular orbitals is there means like this is there. Now I will take N2 molecule. For N2 molecule, how the energy of molecular orbitals is there means here some correction is there. For N2 molecule, how the energy of molecular orbitals is there means here some correction is there. Sir, for N2 molecule, how the energy of molecular orbitals are there, that we will see. Sigma 1s less than, sigma star 1s less than, sigma 2s less than, sigma star 2s less than, pi 2px equal to pi 2py less than sigma 2pz less than pi star 2px equal to pi star 2py less than sigma star 2pz. Okay. Now see, for N2, how the molecular orbitals energy level is there, you see. Sigma 2pz comes here. This sigma 2pz goes to this place. This sigma 2pz goes to this place. Okay. Energy of pi is low, energy of sigma is high. That means what we discussed so far, that is reverse. Reverse is there. But this order is okay for F2, okay for O2.